Hello, everyone. So today we're going to be talking about that most infamous of topics, the notorious PIB. It's time for some particle in a box. So far we've already addressed the idea of what happens when we have a free particle moving through a vacuum. However, it turns out that in chemistry, a lot of the systems we really care about are going to be confined to some set location. Classic examples are electrons on a bond or around an atom. So one of the simplest descriptions of a trapped particle is what's called the particle in a box. So the idea here is that we're going to still be dealing with a free particle. So this means a potential of zero, but that's only going to happen with inside of a box of essentially length L. From 0 to L, potential is zero. Below zero or above L, our potential goes to infinite. Now, what it means by an infinite potential is that a particle would have to have infinite energy to exist outside the box. And as a result, we're only going to see it within this given length. But inside this given length, it's going to have our typical the same typical behavior as a free particle. Same Hamiltonian, only kinetic energy, potential won't play a big role. However, one of the biggest things that's going to differ in between the particle in a box and the typical free particle is that now we have a couple of key features come into play. The first of which is we're required to have a continuous wave function. And we know that outside the box, the wave function has to be zero, just a flat zero. So we're going to need to make sure that our wave function has a value of zero at 0 and at L. So it needs to essentially trail off to zero here and here. However, it is worth noting that we are going to have a discontinuous first derivative, which means we're going to have a slope and then it goes to flat. So the first derivative will have a discontinuity, which is typically forbidden, but it is worth noting that the technical languages of needing a continuous first derivative is only in regions where the potential is non-infinite. So if we go from a non-infinite potential to an infinite potential, this is one of the few cases where we're allowed discontinuity in our first derivative because we have discontinuity in our potential. So we're going to be using these as essentially constraints on our possible wave function. So now we need to choose what's a good wave function for our particle in a box. So a good place to start is, well, inside the box, I'm a free particle. So we're going to do the most general presentation of the free particle wave function. I've got some forward momentum and some backward momentum. Not sure about the ratio of the two, but this is, again, a good general place to start. And it is worth noting that as long as our k's are identical, we have a single energy eigenvalue, which is also exactly what we're looking for. However, this won't be the most convenient way to present the material. So one of the things we can do is turn this into our trigonometric functions. So here comes in our good old Euler's identity. So we can go ahead and substitute in for our positive k, and we'll have cosine plus our imaginary sine term. And then we're going to go ahead and use our negative k, which gives us a cosine and a negative imaginary sine expression. Then what we can do is rearrange this to combine cosines and combine our sines. So these have a shared coefficient. These ones have shared terms inside the cosine, and same thing with the sine. So that makes combining fairly easy, but they have different coefficients. So this means that our cosine is now going to be a plus b, and our sine is a minus b, again, accounting for this imaginary component. Now, let's be honest, this is a little bit messy. So what we're going to do is simplify this expression a little bit and saying that this first time is going to be just a plus b is going to equal c, and a minus b is going to equal d. Now, it is worth noting that this does not mean that d will be imaginary, because it's entirely possible that a and b will be imaginary, at which point we'd have a real value for d. But it does indicate that we would expect if C is going to be real, then D is imaginary and vice versa. Otherwise, you can get almost any value out of C and D that you would like. Again, based on your choices of A and B. However, this just gives us a general form of what we can expect out of our wave function. Now we need to go ahead and put in those edge constraints. So we know that our wave function has to have a value of 0 at x equals 0 and 0 at L equals 0. So let's go ahead and start with this first one because this is a nice one. So what happens when I put in x equals 0? So in this case, let's start with the sign because that one's easiest. Sine of 0 is going to be 0. So this whole term will drop out. However, on this side, I'm left with cosine of 0, which is 1. So it turns out there's only one way to get a wave function of 0. C has to equal 0. So that means that all I'm going to be left with is my psi has to equal d sine k. Now I have to go ahead and figure out, all right, what's going to be my value of k? So this is where L comes in. Because if x is equal to L, I need something where sine of KL will equal 0. Well, the only way that sine of KL equals 0 is if k is some integer of pi over L. Because if it's, say, pi over L, then that would reduce the sign to just sine of pi. That's equal to 0. Sine of 2 pi is equal to 0, 3 pi, 4 pi, 5 pi. So as long as k is some value of some integer times pi over L, we're good. So what we're going to be able to do is describe our general wave function as d times sine n, which is just an integer, times pi x over L. Now, one of the things I do want to acknowledge is that for our choice of n, here we don't exactly want to have n equals 0 because this would mean that I'd have a flat wave function. So psi would equal 0 at all points. Well, that's not exactly realistic because if I have my psi is equal to 0, that means I don't have a particle anywhere. So n equals 0 is impossible, but as long as it's an integer value of 1 or greater, this wave function should work. However, that does leave us with one mystery variable, and that's going to be d. So d here is just going to be a normalization constant. So we know most of our classic strategies to try and normalize a wave function. We can go ahead and apply them here. So what we're going to want to do is integrate our system over all space, which in this case is just 0 to L. And at that point, it should equal to 1. So we can go ahead and input our value of psi into our equation. However, it is worth noting that here we are lucky that we're assuming that d is going to be a real value, so no imaginary numbers. And if we do that, then, well, we don't have to worry about complex conjugates. That's a big blessing. So then what I can do is start combining terms. D, as a normalization constant, should be able to be a constant, be able to be pulled out forward. And that just leaves us d squared times the integral of sine squared n pi x over L over, again, 0 to L. So we're going to set that equal to 1. Now what I need to do is go ahead and evaluate this integral. So again, here we're going to go to our good old integral tables because they're pretty much our lifesaver in this class. So when we do that, we're going to find that this is going to give us x minus 2 minus L over 4 pi times this whole sine term from 0 to L. So then we can go ahead and evaluate each of these terms individually. So let's go ahead and start by evaluating the 0. So if I plug in 0, this value is going to be 0. Sine of 0 is going to be 0. So the whole expression drops out for the 0 term. That leaves us the easy part, which is just plugging in L. So we're left with L over 2, and then sine 2 times some integer pi L. So that gives me L over L, 2n pi. Well, that's just going to be 0 as well, no matter what that integer is. So that means that this whole expression just simply drops down to d squared times L over 2 is equal to 1. So I can go ahead and rearrange that and solve for d, and we're going to find that our normalization constant is always going to give the value of the square root of L over 2. Now, one of the very cool features of that is that this does not depend on what our integer is. No matter what your integer is, we always have the same normalization constant. We love the particle in a box for this. It makes things a lot more simple. So we now have a general function for a one-dimensional particle in a box. Now here come our operators. So we can start by applying our free particle Hamiltonian to the system. So again, this is just going to be h bar squared over 2m times the second derivative of our equation. When we do this, we're going to get, lo and behold, the same energy eigenvalue we did for a free particle, because it's the same Hamiltonian. So this still gets us back k squared h bar squared over 2m. So same value we had for a free particle. The biggest difference here is going to actually be what our k value is, because we've now constrained our k to n pi over L. So when we plug this in, this gives us an energy value of n squared h squared over 8 ml, ml squared. And you may wonder where the pi essentially, where the h bar became an h. Well, the answer is actually fairly straightforward. We introduced essentially a number of pi's along the way, along with the k. So remember, h bar is the same as h over 2 pi, and well, we introduced the pi's, they cancel out. Thus, we go from h bar to simply the Planck's constant. So doing this, we now have a series of energy levels for a particle in a box. So what we've done is we proved that if I have a particle in a box, no matter the size of the particle, no matter the size of the box, the energies are always going to be quantized. And then we can essentially bring the whole system together. And what you're going to notice is that the energies are going to be very tightly packed at the beginning and very sparse as we go to higher values of n. However, one of the things that is worth noting, if we are dealing with high masses or large boxes, what we're going to find is that these particles are, these energy states are going to essentially bleed together so much that it's going to look classical in nature, where there's going to be no gaps in between our energy levels. And again, this brings us to our question of what values of n are allowable. So we know that n has to be a integer value, 1, 2, 3, 4. But if I have a value of 0, well, what this would then mean is that I have no energy or no kinetic energy. And it turns out that we've already established that if I'm dealing with a particle like an electron, it always has to be in motion. So it always has to have some value of kinetic energy. And so a value of, so we need to have a, so our lowest possible value is 1. So this means that a particle in a box always has a ground state energy. It always has some sort of intrinsic energy. And we can get the energies of excitation, so the energy to go from one level to another, essentially given by our constants, h squared over 8 ml squared, times the difference of the squares of the corresponding energy levels. And again, this means that I can then take this energy to figure out what wavelength of light would be required to drive that excitation. And again, worth noting that the wavelengths of light required can be controlled by the mass of the particle being excited, often an electron, and the length of a box. So again, it's also going to be fairly worthwhile looking at what the shape of these behaviors are. So if I have a classic particle in its ground state, n of 1, we're going to have a nice kind of smooth behavior with most of the particle being located in the middle. and a probability density that is a little bit more edged and brought together. However, when we go to the n equals 2, we notice that we have a positive wave function on one side, negative wave function on the other. However, when we go to probability density, we tend to find that that most of the probability is now moving towards the two sides. We're more likely to be caught near the edges. And again, this is essentially emphasized as we go towards towards the third, fourth, and fifth energy level. So we can also use this, now that we have a wave function, to determine the probability of finding a particle in any point in the box. So a classic trick is trying to find the probability of finding the particle on the left side of the box. So I'm going to try and determine the probability of finding the particle between 0 and L halves. So we do this same way we did kind of with normalization. The only difference is now we changed our value from 0 to L to 0 to L halves. I like using the 0 because, as we saw before, most of our terms end up just dropping out. And then what we're mostly left with is the L halves expression. And again, what we have here is if I have L halves, I'm still left with values of n pi. So again, no matter what our n is, this will still end up dropping out. And all I'm going to be left with is L halves over 2, or L fourth, times my normalization constant. So this gives me 1/2. So it turns out I've got a 50% probability of found on the left side of the box. And notice that this doesn't actually depend on what energy state I'm looking at. This will always be the case. And hopefully you can kind of inspect that when looking at all of our wave functions kind of visually. Not too surprisingly, as we've shown before, it also turns out if we're trying to find the expectation value of the system, the particle is also going to have an average location of the middle of the box, because I have just as much of my density on the left-hand side as the right-hand side, no matter the n. So this kind of brings us to the end of the one-dimensional particle in a box, but it's worth acknowledging that we're going to need to extend this to 2 or even 3 dimensions. So next time, we're going to go multidimensional. Until then, take care.